So a relation is any relationship between two sets of numbers. It can be like an equation where y equals 2x, so every time you take an x and you times it times 2 and you get a y. It can be just something that you've written down. You can just write down random sets of ordered pairs and pair up numbers however you want. And that's also a relation. It's just any kind of a relationship between two groups of numbers. Okay. A coordinate system is made up of a relation between numbers in a set x and a set y. Usually that's the real numbers. Usually when we're talking about a coordinate system, we're talking about every real number, but not always. The ordered pair is the way you show a relationship between one pair of numbers, one x and one y. And it goes alphabetical, x, y. And you don't have to necessarily use x and y. We can call this coordinate, or this line A and this line B. And so we'd have the ordered pair A, B. It's always alphabetical though. So the x coordinate is the first number. It's also known as the domain element. And the y coordinate is the second number. It's also known as the range element. Okay, x is horizontal. So this axis right here is the x-axis. Y is vertical, so that's the y-axis going up and down. The best way I know to remember that is that y goes more up and down than x does. Like y has a tail, so kind of y does go up and down, like the actual letter, so does the actual axis, if that helps for you to remember which is which. Okay, mapping, oops. A mapping is like, it shows the relationship between the numbers in the relation. It's visual. Okay, like maps are visual. Okay. The domain is the first set of numbers. The domain is the input. These are the numbers that you can plug into the relation.
Wait, what?
Input. You would put, these are the domain is the first group of numbers, and it's the numbers that get put in.
Like,
plotted? Plotted is, you plot the domain and the range. Like when you're plotting a ordered pair,
right.
The x is the domain, the y is the range.
Oh, okay.
But so if you have like an equation, you pick x's, you plug in x's, and you get out y's. Does that make sense? So like the domain is like the ingredients that you put into the bowl, and the range is the output. This is the cake that you get when you're done.
Okay, that's cool.
Okay, so and that's the second set of numbers. So the domain is the input, the things you put in, and the range is what you get out. So like if you're baking a cake, the domain would be like eggs, milk, sugar, flour.
You give like a numerical example?
Yeah, like if we have an equation, so say y equals 5x. Okay, I can pick any number from the domain. Pick a number. 4. Y equals 5 times 4. So y is 20. Input, output.
Oh.
Okay. The domain is also...
Could that work the other way too?
You can pick y's, but you're limited. Every x would work here, right? I could plug in.
If you knew the y, you had to find out the x.
Yes, you can do that, but it's limited because every single any x, I can throw in any x in the whole wide world here, but I can't necessarily throw in every y. Okay, these are called the independent variable. Yeah, and these are the dependent. Doesn't have a D at the end, it has a T at the end. Okay, because it's X, the domain is independent. I can pick any domain variable I want. I can pick any number I want, plug it in. That's input. The output is dependent on what you put into it. So cake, I'm making cake, right? If I put, the flour and the eggs and everything and sugar, I get a nice yummy cake. If I put in everything and salt,
Yeah, and then
yuck, right? But my cake, like the quality of my cake depends on what did I put into it. So there's a couple different ways to represent a mapping. You can do a set of ordered pairs. Okay, so just a set
that's gonna be how quite a
of ordered pairs. You can do a table. You can do a coordinate plane. So we can actually graph the dots, right? So 1, 1, 2, 3, 2, 3, 4, 5, 6. 6, 8, 5, -4. Or you can do what's actually called a mapping. Now when you do a mapping, it's kind of nice because you actually have the domain separated and the range separated, all nice and neat for you. And then you draw an arrow to show which numbers go with which. Okay, so we're going to express this as a table, a graph, and a mapping.
Some space for that.
Sure there is. Table, you just do X and Y like this. And I'm going to list my X's. And then I'm going
Do you have
to...
to list them in order of like how it would be on the scale or something?
Nope, I'm just listing them how they came here. So there's my table. Now I'm going to do my graph, so I'm just going to make my graph. You can see it's not perfect, but it's more about the concepts than the perfect spacing right now on the notes, So, okay, when you're graphing these, you always do your X value first, so I'm going to go 2, 5. So I go over 2 and then up 5. -2, 3, so I go back 2 and then to 3 on the Y. 5, -2, so over 5 and then down 2, and then -1, -2. Okay, and then the mapping, I usually just put a D and an R for domain and range. Write the numbers. Draw boxes or ovals around them. And then put arrows showing which number goes with which. Great, thank you for catching that. You should only write this once.
So you just point the arrow up to that too?
Yeah, so that was my mistake. You should, when you're doing a mapping like this, you only list each element once. So this -2 showed up twice, so I list it once, but it has 2 arrows going to it. So that was my mistake. I'm going to blame. Main is all the set of the X's. So So we just list them. And again, you're listing each number once. So the range is the set of all the y's. So
We do it in order? Or is
you
it-
don't have to. You can. This. The independent variable is the x value, or the domain variable. And it's independent because this is what you pick.
This one gets picked.
Dude. Keep correcting the teacher.
Okay, so this is what gets picked and put into the relation. So this is like the ingredients that you stick in the bowl. And then the dependent variable, again, is the y value, or the range variable. Okay, this is the output. Okay, so whatever you pick, you put in. The dependent variable, the range, is what comes out. And it depends on what you put into the relation. Like I said with cake, if you put sugar in, yum. If you put salt in, yuck. Actually, you do put a little bit of salt, so it fluffs properly, but just a little tiny bit of salt. I mean, it would be like if you replaced the sugar with salt, that would be yuck. Okay, so if we're identifying independent and dependent variables, dance committee is selling tickets to the fall ball. The more tickets they sell, the greater amount of money they can have for, or they can spend for decorations. Okay. Which thing depends on the other?
The decorations depend on the ticket.
Right, the decorations depend on how many tickets they sell. So the decorations then is the dependent variable.
Which is
Right, so we can say ticket sales are independent. Decorations are dependent. Okay. If we look at B, the average price of going to the movies has steadily increased over time. Which one of those depends on the other?
So depends on time. Or price depends on time.
Price depends on time, right? So time is the independent variable. And time is almost always the independent variable.
That's just what time.
Yeah. Because time just happens.
It's inevitable.
Mm-hmm. And movie price is dependent. All right, so a function is a special type of relation where each domain value only has one range value. So for every x I plug in, when I plug in x, I only get one number out. I don't get two numbers out. Does that make sense?
What do you repeat?
So if I plug x in, I just get one answer, not two, just one. So if I plug in -2, I get -3. If I plug in 0, I get 6. If I plug in 3, I get 6. That's okay, because 0 didn't give me 6 and say 9. 0 just gives me 6. 3 gives me 6, 4 gives me 9. Here, 1 gives me 4, 3 gives me 2, 5 gives me 4, -1 gives me -4. I don't have like 1 giving me 4 and 2. 1 just gives me 4. Here, if I look, this x only gives me this y. There are no other y's for that x. This x only gives me just this y. Same here, same here. I don't have two y's on the same x. if, yeah.
But I don't get it. There's a 0 and a 6.
And 3 can go to 6.
So if you're plotting it, where is it on the 0?
0, right here. So it would be 1, 2, 3, 4, 5, 6.
Oh.
0, 6.
Okay, I didn't know.
And then 3 would be 1, 2, 3, 6. But see, it's the same. It's okay because I have x's where no other y's are on that x. What would make this not a function is if I came here and I put a dot like that. And see how there's 2 y's for that same x? That's not okay.
Where does the y come from?
Usually it comes from an equation. And there are some equations that will give you 2 x's. Y equal, oh, that's green. Green doesn't show up good, sorry. If I say y equals the square root of x.
You type it.
If I plug in a 4 here, the square root of 4 is 2 and negative 2. Does that make sense? So this is not a function. Because if I plug in 4, I get 2 and I get negative 2 because both of those are the square root of 4.
I see. So it'll give you an equation. You just plug numbers into it and find out if it's a.
Well, no. We're going to talk about like a picture version of this too. But you were just saying this is an example of an equation that can give you 2 y's.
All right.
Okay. Does everybody have this page?
I have a question for you.
Mhm.
Where did that table come from down there?
Here?
Yeah.
I just made it up.
Oh, okay. So. Okay.
Now your T tables it can go sideways or up and down. I just did it sideways because of space. Okay. So to determine whether a relation is a function or not. Well, let's look at that one that we had on the previous page. Oops. No, that's not the one. I'm looking at the wrong one. Sorry. -2, 0, 3, 4. And then my range is -3, 6, and 9. Okay, here's the test. What I do is I look right here. Only on the domain side. And I count the number of arrows. Okay. I have 1 arrow, 1, 1, 1. Okay. I only have 1 arrow each, so this is a function. Okay. If I take a different table, let's say. What I can do, there's a couple ways I can do this. I can either look at this table and I can say I can have 2 different x's, or 2 x's that are the same with 2 different y's. Or I can draw a real quick mapping, but when you do that, you only list each one once.
So that's not a function.
Right? Yeah. So when I come and I do my arrows, I'm going to, okay, 0 goes to 3, 6 goes to 8, 0 goes to -2. I have 2 arrows right there. So it's not a function. So a discrete function is a function that's made up of a set of individual points. They don't connect. A continuous function is like a line or a curve of points that flow into one another. If you want to think about it, if I have a jar of marbles, or jar, right? It's empty, and then today I throw in a handful of marbles. Say I threw in 5. So now my function point would be like day 1, 5 marbles. So it would be like 1, 5. And then day 2, I throw in 5 more marbles. So then it's 2, 10. Day 3, I throw in 5 more marbles. So it's 3, 15. But you see how it's individual points, kind of throwing in 5 marbles at a time. So it doesn't flow into each other. A continuous function is a line that flows into, the points flow into each other. Growing is a continuous function. When you're growing as a child, it's not like today you're 3 feet 2 inches, and then in a week, like next week, you go to bed, you're 3 feet 2 inches, you wake up in the morning, you're 4 foot 8. Right? You didn't just jump a foot one day and you're suddenly instantly the next day. It's a gradual height. Your heights flow into each other. So maybe you don't measure yourself every day and you're like, I grew another 1/18 of an inch today. But as you measure your height over time, you draw a line connecting the dots, because in between the times you measured, you were still growing. Does that make sense? So continuous functions are functions where things happen and they like smooth into each other or run into each other. So if we have an ice sculpting contest and each sculpture's height was measured to make sure it was in the regulated height range of no feet, which is kind of silly if you think about it, because how could you have a no foot tall ice sculpture, to 6 feet. Okay, the measurements are as follows. Team 1 is 4 feet. Team 2 is 4.5 feet. Team 3 is 3.2 feet. Team 4 is 5.1 feet. And Team 5 is 4.8 feet. Okay, did I leave a blank spot for you guys? Yes, I did. Okay, so what we're going to do is you're going to come to this next page, and we're going to make a table. Okay, we have 5 teams, so those are going to be my X values. And each team made an ice sculpture. And the heights are as follows. So team 1 was 4 feet, team 2 was 4.5, team 3 was 3.2, team 4 was 5.1, and team 5 was 4.8. Okay. So that was A. B asked us to determine the domain and the range. So the domain and the range. The domain is the team numbers. The range is the ice sculpture heights. Okay. C is we're going to convert the data to ordered pairs. Okay. Then we're going to graph them. Now, nice thing about graphing, when you're given a piece of graph paper with no set X and Y coordinate, you can put the X and Y coordinate where you want, so it would make sense. I have only positive numbers. So I'm going to put my X and Y coordinate not in the center, but low and to the left, because I only want positive numbers, so that's all going to be up in this corner. Okay. 1, 4. All right, first I need to determine my range because I have decimals on my y's, and I'm going to spread it out. So I'm not going to say this is 1, this is 2, this is 3, this is 4. I've got 5. So this is going to be 15 lines right here. So I'm going to say this is 1, 2, 3, 4, and 5. Actually, that's probably going to, no. I'm going to do 2. 1, 2, 3, 4, 5. Because we do go over 5 there. So now I'll do the same thing this way. 1, 2, 3, 4, and 5. Team 1 sculpture was 4 inches. Team 2 sculpture was 4.5. Team 3 is 3.2. So 3.2 is just slightly above 3. So just put a dot slightly above 3. 5.1 is slightly above 5. And then 4.8 is slightly below 5. Okay, that was D. Sorry. And E asks us, is this going to be a discrete or continuous function? Are the heights of the ice sculptures from the individual teams going to like melt into each other and bleed in?
Individual.
They're individual, right? It's individual sculptures with individual heights, so that is discrete. And I know it's a function because no team had the same height. Like if team 1 had been 4 feet and team 4 had been 4 feet, then it wouldn't be a function. But this is a function because none of the y's repeat. The feeder weighs 2.3 pounds when empty and 13 pounds when full. So I'm going to make a table real quick where I have 0, 1, 2, and 3 quarts of seed. And then I have the weights. Okay. For B, that list is the domain, that list is the range. Ordered pairs. Okay. And now I'm going to graph this. Oh no. Sorry, I messed that up. Yeah, I did 3. I was doing my X's on my Y for some reason. Okay, then on here I'm just gonna, because it's 13 and I have 15 boxes, I'm gonna make each one of these 1. Okay. So at 0 pound or 0 quarts of seed, I weigh 2.3 pounds. So that's somewhere halfway between 2 and 3-ish. At 1 quart, I weigh 6 pounds, so I've got to go up to 6. So 1, 2, 3, 4, 5, 6. At 2 quarts, I weigh 9.7, so that's almost to 10. And then at 3 quarts, I weigh 13.4. So it's 10, 11, 12, 13, and then like halfway above that. Now, Do you think that the bird comes and eats an entire quart of seed like instantly in one gulp? No, the seed's going to gradually get emptied, right? A little bit at a time. So is this going to be a set of points like this, or do I need to connect those with a line? Do they flow into each other like the weight of the bird feeder?
Yeah.
Yeah, it's going to flow into each other. So I'm going to connect those with a line. And so it's continuous. Okay. So things that are commonly continuous are things like weight.
What about linear equations?
We'll get there.
Okay.
But like weight changing over time, weight is kind of a tough one actually. Weight, if you're talking about weight changing over time, that's continuous, but if you're talking about like one book weighs this much, 2 books weigh that much, 3 books, that's discrete. Growth is continuous, but height can be discrete. So it's just kind of look at the values of what you have. Okay, vertical line test. This is a way to tell from a function if you have a picture. If you're given a graph and you need to tell whether it's a function or not. Okay, the vertical line test says this. If you draw a vertical line, so that's up and down, right? Through a graph. Okay, so here's what happens. We have pictures, functions, and if we want to draw, or we want to tell quickly if it is a function or not, we're going to draw a vertical line through the graph and then determine if that's a function or not. So let's say I have a graph that looks like this. Okay. Maybe I have one that looks like that. And I can also have one that has an open circle and a closed circle. Okay. Now if I take a vertical line and I move, not the graph, but the line. Stop moving the graph. If I move this, that's not what I want to do. Okay, see how I'm moving it? As I move this vertical line across, do you see how it's only touching the graph in one point at any given time? Okay, this is a function. So that's a function. If I take it and I come over here, right here it touches at one point, but as soon as I go over here, it's touching at 2 different places, here and here. Okay. Now, this one is a little tricky. So far so good. And then I hit here. And it looks like it's touching at 2 places, right?
What is an open circle?
But it's an open circle, so that open circle doesn't count. So it's still only touching at one place right here. So it is a function. Okay, so if you have that where you get a dot and an open circle, then you're okay. But if these were both closed circles, then it's not okay. The easiest way to do this is if we move this 3x over here so I get y equals whatever. And I can pick this 3x up and I can move it over here. if I do that, I cross the equal sign, so if I change sides, you change signs. Okay, and if you think about that, if you're like on one team and your colors are purple and yellow, you have a purple and yellow jersey on, right? But then if you go and you're traded and you get on another team, you don't still wear your purple and yellow jersey. You wear the blue and gold one that they gave you. So change sides, you change signs. So if I pick this up and I move it, it's now positive. And that'll just make it easier for doing your table. I always like to put in 0. 0 is nice because 0 makes things go away. So if I plug in a 0 here, I get 8 plus 0. So that's 8. Right? If I plug in a 1, I get y equals 8 plus 3 times 1. So that's y equals 8 plus 3, so that's 11. It's kind of big. I don't want to graph that high, so I'm going to throw in a negative number. Negative 1. So I get 8 minus 3, which is 5. You only need 2 numbers to graph a straight line, 2 pairs. So if I do 0 and 8 and negative 1 and 5, if I say that this is 2 and this is 1, negative 1. So 0, 2, 4, 6, 8. And then negative 1, 2, 4, 5. And I connect the dots. Am I going to pass the vertical line test? Yeah, I passed every vertical line down this is only going to touch once, so yes, it's a function. So f of x, if it's there, that tells you automatically it's a function. You never have to test to see if it's a function. You can't use f of x if it's not a function. So instead of saying y equals negative 4x plus 7, we have f of x equals negative 4x plus 7. So then f of 2 means that I'm going to take 2 and I'm going to plug it in. So f of 2 is equal to negative 4 times 2 plus 7. So that's negative 8 plus 7. So that's negative 1. So I can say f of 2 equals negative 1. So whatever is in here gets plugged in. Now here I have f of negative 3 plus 1. So what I have to do is I have to plug in negative 3 for x. And then I also add 1 to the end of the function. So f of negative 3 is, hold on. So I take that negative 4x, I replace it with negative 3 plus 7. That's replacing it. Then I also have to do this, plus 1. For this plus 1 that's right there. It just gets tacked on to the end. Does that make sense?
Is that an x plug in negative 3 for x?
Yes. So then I do this and I get 12 plus 7 plus 1. So that's 20. Okay. So the f of negative 3 shows me that the negative 3 gets plugged into f of x, and then the plus 1 shows me that I tack on a plus 1 at the end. Does that make sense? Okay, f of x is this part, right? So f of negative 3, just if I just had the negative 3, is this part. Where I took this x and replaced it with negative 3. But see how it had this plus 1 on the end? That's why I threw a plus 1 on here. So just It's just like an add-on. If I said 2 times f of 1 or something, that would be, I would take that -4 times 1 plus 7, but then I'd multiply the whole thing times 2, because that 2 is outside. So anything happening outside of the f of whatever number is just like add-ons.
So you replace the f with 3?
You replace the x. Whatever's inside the parenthesis here on the f
All right.
is what replaces the x. So here it was 2, so we put a 2 in where the x was. Here it was -3, so we put a -3 where the x was.
I see.
Let's do a couple more. So h of t is all this, right? I want to take h of 4. So if h of t okay, so h of 4, I'm going to take, everywhere there was a t, I plug in a 4. Have my 68s memorized. I think that's 256, but I should check myself. Yes, 256. Except it's negative. So that's 16 plus 2, so that's 18. Now here, again, h of t, except we're looking for h of g. And then we're going to multiply it by 2
When will we use this?
later.
Like in life, what profession is this used for?
If I just do h of g, what I do is everywhere there's a t, I replace it with a g. I don't know why, just because they said so. But see how I had this 2 on the outside? That means I'm going to take what I just did and multiply it all by 2.
Dude, this is really weird. Yeah. I thought this was algebra 1.
It says Algebra 1.
I've never even seen this before.
Hold on 1 second.